So welcome back. Let's first.
Everyone is on the same page. Everyone has model.
Yeah, so actually, my COMSOL stopped just now. Let's see what I get when I recover. If not, I will. Okay. Yeah. So I have.
Okay, guys. So everyone is on the same page. Yeah. So everyone has created a model with all these symmetries, with the mesh. No problems for everyone. Yeah. Okay. So everyone now can calculate at least one mode. Yeah.
Okay. Okay. So now, adding the parametric sweep basically adds a second data set, and adding a second data set to the COMSOL model adds a second plot group. The other thing you can do basically is here, if you are in the first plot group here where we have these nice little arrows, you can zoom in here. Looks like that. Then here, study one, solution one. So this solution, that's the solution we did before, yeah. So I can go here. I can go to parametric solutions. So study one, parametric solutions, solution two. And this allows me now to see, within this plot group, I can now see the data that I have calculated during the coffee break. And so I have only one mode, yeah? But I have a bunch of different frequencies, yeah? From 125 to 375. And so when I plot this, pressing F8, I can plot this. And if I alternate with the arrow keys and with F8, I can basically now quickly browse through all the frequencies, and I see how this modes, of course, will change and how the evanescence field will increase when I increase the wavelength.
So did everyone apply parametric sweep?
So
parametric sweep? Did you apply it?
Yes, yes.
So you can all get. You should all basically now have the identical data on your laptop.
Only my arrows are gone.
Your arrows are gone?
Yeah.
Because you're here. You're in this plot group, and the other plot group. Yeah. So this is a second plot group that is created by running the parametric sweep, which doesn't have the error surface. So if you duplicate it and you pull it down here, you replot, you will also get the error surface in the other plot. Yeah, but this. But you can also change which data set to display in the first one. So this should work. Okay. Now we have all these values. Now we need a way to export them, and the way to export them is basically we need to put these values into a table, and then we can export it to a text file and reload it in MATLAB, for example. So basically, you go here. You go derived values, right-click, and then you take a global evaluation, and you put an expression in here. So first of all, we need the parametric solutions, all frequencies, all mode indices, and the expression we need to use is EWFD.NF. Okay, there is a funny E. So, and it knows that this is the effective mode index, okay? And now I can do here, wait a second, where I can right-click here and I can call it to evaluate onto a new table. So I do that. And now it just mines the data basically from the solutions and puts it into a nice table for me to reuse. Okay, now sample frequency. It added this lambda. And then here I have the effective mode index. So the effective mode index ranges from 165 to 196. And some of them have a very small imaginary part, where you basically get some spurious absorption in the metal boundaries. Don't worry about that. That's 10 to the minus 16. So that's basically yeah, the absorption you get by crossing the universe once. So.
I don't have any imaginary parts actually.
Well, that depends. Maybe I have. That
So my lambda is quite different.
Your lambda is quite different. That is.
Yeah, lambda is also quite only real partition.
No, near part. Yeah, again, don't worry about this imaginary parts. That's basically a totally negligible absorption. I mean, you talk. I mean, even if you calculate n squared plus k squared, yeah, that's 10 to the minus 26. So please.
Yeah, okay, but my lambda for
The lambda is not. Huh?
It's 1.84.
For what?
For the first 125.
1.84.
Yeah.
Oh, you know what you did. Are you sure that you did in the geometry that you did this? That you halved the width of the waveguide in size? You probably didn't do that.
No.
Yeah, so your waveguide is now twice as thick. Don't worry, no problem. No need to recalculate. I will just now show how it would be done in principle. No need to recalculate. Yeah. So if you get slightly different values, so we have one case here where what's your name? Roel. Where Roel basically forgot to halve the widths and heights of the waveguide, so he basically now calculated a structure that is twice as big, and of course the refractive index will be quite a bit different for that. But this will still this still gets you fundamental modes. This will still get you dispersion, and it's probably going to be anomalous. So there's absolutely no issue. Okay. So can everybody generate some form of this table?
Yes.
Okay, good. So now I can export this table using the export button. So here is an export button.
Yeah.
I think we just missed this.
Yeah.
Oh, we're just having trouble with the table.
I'll just continue. Otherwise, we can't progress. Okay. So now you can export this stuff. I'm going to export to our Dropbox. Straight waveguide. Okay. Now I have all this data available to make plots basically, and so there's 2 more questions that came up. There's 2 more questions that came up, and I want to address, and that is how to actually calculate, how to actually check which modes are there, and you could do it in an automated manner, and the other thing is how to calculate the effective nonlinearity of the system. And so the effective nonlinearity of a 4th order dispersion waveguide is the effective area is this formula. It's this formula. Most of you should maybe have seen it already. That's how you calculate the effective area that you need to calculate the G0 that Alexei will introduce later. So this basically follows from the derivation of the nonlinear Schrödinger equation from the Maxwell equation. Okay. So now the question is, how can we calculate this type of variable from COMSOL? That's the question I want to now quickly answer. And the way you do that is basically you need to include what's called a probe, and a probe is basically a way to access something that's hidden in the calculation, and you want to make it accessible for you. So basically, you hear definitions, and in definitions you can include variables, and you can include probes. And the thing we need is a domain probe. Domain probe. So domain probe again has a domain variable. It shows you where it's active. Yeah, it should be active in the whole field. And then you have different things here. Basically, average. What we need is integral because we wanna calculate an integral down there. And the thing we wanna calculate is basically the square of the electric field on the full field. So basically, I have here an expression which is called norm E. This basically is just the absolute value of the electric field. And you can actually, the way it's calculated, you can look up in the equation view. Yeah, in equation view, if you look at norm E, you see that it's the square root of the field squared. And everything has a unit. So this is volt per meter. So you see it has the unit of just field. And volt times meter. Yeah, so you have field volt per meter times meter squared because you calculate the integral. And so this thing I just need squared basically. Sorry, German keyboard. So this thing just squared. Now you get the updated unit, where you basically have the calculation into kilogram and ampere. So the calculation. So when it doesn't know how to transfer the volt anymore, it goes directly to SI units. And that I basically the variable name of that I call norm E squared, and I use the same as a label usually. So this simplifies the things, and I duplicate this. Yeah. So right click on this thing and I duplicate it. And then I get the same again, and now I need the same for the fourth order of the field. I call it quad. And I put to the power of 4 in here. Okay, now I'm here. And so now basically I have these two additional variables to work with. Yeah. I have these two additional variables to work with, and I can use here the update results. So from the saved data now, it will calculate all these integrals, and that now goes pretty fast. So I don't need to resolve the whole structure. And here down here, I now have these things. I have these additional evaluations. And so I want to make another global evaluation to calculate the effective field. So I will actually call this effective index, just to keep a bit of order in here. And this I call effective area. Okay, and then I can put in an equation here. And so the equation is basically that the norm E squared that I calculated squared divided by the norm E quad. So norm E squared divided by norm E quad. Wait. That should have a unit actually.
How do you get the effective area? That's like a new global evaluation.
A new global evaluation, exactly.
Yeah, okay.
And now try to evaluate it. And we want to evaluate it into table 1. So it complains about the non-calcul. Okay, maybe I need to recalculate actually in order to get this. So it will disable the parametric sweep, and then I can recalculate the mode analysis for a single frequency. Okay, and now in the table, just okay. So there's a second way of doing that. You put the global variable probe in here. We call it the effective area, and here you can put in the same norm E squared times.
I didn't get it.
It doesn't matter. I'm just showing it now. The norm E quad. So this now has a meter squared, and if I update the results on that one, then no, it takes a time. Oh, this does now the parametric sweep. Okay. Also very useful when you do. No. Okay. Okay, now it updated all this. I get effective area 2. Huh. For some reason now it worked. Okay. So delete that one. Okay, now I have here effective area 2. And basically I get another table. I get another table that tells me now the effective area of these in meter squared. And I can actually, what I can do is I can put in micrometer squared here. If I change this to micrometer squared and evaluate again, I get the value in micrometer squared. So,
Johann,
yeah.
you didn't change the data set for effective area?
No, I didn't.
You use probe solution.
Here is the solution. That should not. That should be set automatically, actually, but this is not so important right now. So now I can go into MATLAB. And so I prepared yesterday evening. I prepared a solution that I'll also share. I prepared a solution, and here it's called microring 50 micron. No, that's microring and straight waveguide. Straight waveguide dispersion. So basically, I have prepared a solution here of the effective mode indices, and I have exported this table, and so from 100 to 400 terahertz. And here I will show you how to get the dispersion now in using MATLAB, for example. But this, of course, also works perfectly with Python. So basically, I have this txt file, and I got straight waveguide script. So now, in the script here, what we basically do is we load this script. We load this txt file. We extract the frequency and the effective index. We're of course only interested in the real part of this effective index to calculate the dispersion. And then from this you can use polynomial fitting to smooth out the data, because you probably don't have so many points. And I using just discrete derivatives for calculating the finite differences for calculating the derivative could be a bit grainy, and in that way you can smooth it out a bit, and then you basically you derive this, you calculate the derivative of this polynomial, and you calculate the derivative of that polynomial to get beta 1, beta 2, beta 3, and so forth as a function of the frequency. And then in order to calculate the phase mismatch, you basically just calculate the beta factor, and you subtract the beta 0, so omega pump, and you subtract the beta 1 times. So the first two factors of the Taylor expansion you subtract, and this gives you the nonlinear phase mismatch. And this should actually just yeah, okay. Wait a second. Wow, nice. That threw me out of MATLAB. Okay. Okay. Okay, let's try again too. Okay. Okay. So here we have the effective index as a function of frequency. That's just the raw data. From this raw data, you can basically calculate the beta. You can calculate the first order dispersion, which is 1 over the group velocity, in the approximation of your polynomial. And from this, you can calculate the second order dispersion. So analyzing the second order dispersion, you will see here you have a window of anomalous dispersion between the frequencies of 160 and 270 terahertz, which is of course what we designed the waveguide cross section to feature. And so if you go to third order dispersion, looks like that. So the reason why this is now a third order function is because I use a sixth order function here to model the polynomial. So if you need a higher precision, you need more points than to use a higher order polynomial. Yeah, so you have to basically check that this works out and is close enough to the reality for your need, or you can use different methods of calculating the dispersion.
So is that always true that higher order polynomial fitting will always give you?
That depends actually, because if you calculate, I mean, you need enough points. I mean, it doesn't make sense to fit 8th order polynomial on 7 points. Yeah, so you need like 10 times more points to make sense, to get a good fitting, good smoothing. I mean, this is nothing else but smoothing the function. Yeah, and you have to be careful, because if you have high order polynomials at the edge of the window, they can really shoot off, and that you want to avoid. And it's the same with low order polynomials. I mean, they might not catch. I mean, at the end, they might just cross over and do something weird. But here again, what you see when you calculate the nonlinear phase mismatch, so that's the last formula I've shown you. You get a curve that looks like this, and this is this shows you that you get that you will probably get a dispersive wave of the super continuum generation in a waveguide like that is emitted about 120 terahertz. Yeah, so that's basically where the nonlinear phase mismatch crosses back over. Okay. So that way, and so that way you can work pretty straightforward with MATLAB. Okay, so now it's a bit time is a bit progressed, so I'll just show you 2 more things. And you can then spend a bit of time in the exercise session, both today now and after the numerical session to check in a bit more if you're interested. So we will be around to assist. So the first thing would be how do you set up a micro ring resonator?
Ring 15 micro.
Yeah, you can open the micro ring. Yeah, here's a bunch of, okay, very nice. Okay, so if you open micro ring 50 micrometer, you will see something like this. So here basically there's one big change. So if you select new model with that, now we use the 2D axisymmetric, yeah. We use the 2D axisymmetric, so to get the cylindrical coordinate system to use for the simulation, yeah. And this will take care of the waveguide bending, basically. Okay, and so basically, no, let's exactly. So if you now look at your modes. It's the modes I have simulated here. You again have electric field 1, so the one which shows the parametric solution. And you just check the parameter value, and you can again basically click yourself through there. what you see is that the mode not only shrinks, but it also moves outward in the waveguide. Yeah. So now you see it pretty clearly that the mode actually hugs the wall, hugs the outer wall, and that's like basically centrifugal force. Yeah. And here it's also like the mode always tries. I mean, the light always wants to go straight, and then it's reflected around the circumference of the resonator.
Effective mode index so tiny.
Yeah, that is because COMSOL has a nice little bug. Okay, so COMSOL actually, what it calculates has the unit. So the beta it calculates has the unit 1/meter. And now you have the radius, yeah. And now basically that screws up the internal coordinate system. So what COMSOL calculates here, and it's also, you'll find it on the slides, is not the effective mode index, but it's the effective mode index times the radius. Yeah. So in that case, 50 microns. So you just, and that is not the effective radius, yeah, because the effective radius of the mode, like the effective propagation distance, is now increased. Yeah, it's not in the center, it's out here. But for the sake of this COMSOL bug, it's really the radius you put into your calculation. Yeah, and there you can even put your zero of the, if you put your zero of the radius here, yeah, if that is your zero in the simulation, actually you need to take this value then. So this is a funny little bug in the COMSOL. So that's why the mode index is so low. And but if you actually look here, I have made an R effective probe, and so R effective is basically this value here. So the square of the field times R, and just the square of the field. And that gives you a R effective. So if you just plot where the actual mode is, give you a probe plot group. Let's look which one it is. Yeah, this one it is. So if I zoom in here to the red one, you will actually see that you actually see how the mode basically. How the mode basically, so this is 50, that's the center of the waveguide, and how the mode basically hugs the wall and how it increases for higher frequencies. Yeah. Okay. And so I've again prepared probe tables for that. Which one is this? The 2, yeah. No, it's the one. This one, sorry. Okay, so here basically you have the frequency, you have the effective index of the mode, and down here you have the effective index times omega over c. So that is basically the azimuthal mode number. You see that the azimuthal mode number is fractional. So what this means is COMSOL doesn't know that this is a resonator, so it calculates a banded waveguide at a certain frequency. This frequency will in general not be resonant. Yeah, it's going to be non-resonant. And so you get a fractional mode number. Is basically how often does this specific frequency fit into the resonator, the specific wavelength. And this being fractional means that the frequency is non-resonant. And but that is no problem for calculation of the dispersion. You can still calculate the dispersion. Yeah, I mean, if you want to calculate the actual frequency, you have to flip around the problem. You have to find a frequency which actually gives you a non-fractional mode number. So you can do that via the integrated optimization routines or using an external optimization routine. Just basically Newton-Raphson optimizing the fractional mode number of the fractional part of this mode number, and then you can find an actual resonance frequency. But for the sake of dispersion calculation, we don't need to know the actual resonance frequencies. We only need to know the relation between the m and the omega. Yeah, because that's sufficient. So, and if you go here, that is the relation between the m and the omega. And so here basically you have the NF times R, which is what the COMSOL computes. The omega you know, and C of course you also know. And if you have this relation, basically the mu is just the m minus m pump. Then from this relation you can calculate all this stuff. And if you do that, or to do that, we can again say here have microring script, and this should also just execute. And now from the microring script, sorry for the missing, sorry, here that is a d-int. Sorry for the missing stuff here, for the missing labels. That's bad practice on my part. Okay, so here, if you see a red and you see very tiny red curve, so that's basically I checked whether or not the polynomial smoothing works. For the amount of smoothing it does, it seems to work pretty nicely. So just that's the offset between the polynomial and the actual data. And you basically need to you can just, I mean, the easiest way to check this is probably just using the d-int. Here is d2 as a function of wavelengths. So basically you again have this d2 window between 165 and 240 terahertz, and you pump here, and then you get a soliton. Okay. So d1, that gives you basically the free spectral range of this resonator, and it varies between, you see, it varies between 455 and 445. So the 50 micron micro resonator gives you about 450 gigahertz. So this can, and this is the most important curve really is the d-int. And so the d-int will basically tell you where this burst of waves will appear, and here it appears at 125, and it appears at 340. For the geometry I've chosen here, and that is, I quickly need to check because I changed it a few times. So the waveguide width is here is no, I think that's the wrong model. That's the wrong model. That is this model, yeah. Because I think I've used quite small. Yeah, so I have a waveguide width which is 2 micron here. And this is basically with a wider waveguide you exemplify this forcing to the sidewall, because as you make the width of this waveguide wider, at some point basically you're close all the way to the inner radius, and you transition your strip waveguide microring to basically a microdisc resonator. And that is only confined now to the wall because of this whispering gallery potential. And in that way, basically, it comes all back to one another. Okay. So that's basically what's required to solve exercise 2, because exercise 2 you should basically take this starting point and try to get this dispersive wave, I think, to 150, if I remember correctly. Yeah. So this is one of the things you should learn in this workshop. And I think we're almost at lunch, so sorry for eating up the. We have 1 hour. Okay. So
it's the beginning of exercise session exactly right now.
Right. Okay. Yeah, I have one more thing, and this is calculate bending losses. That would be exercise 3. I will very quickly show it how it's done. Yeah, that doesn't take long. So I have the bending loss, MPH. Don't need that. Okay. So yeah, how do you calculate bending losses? So first of all, how does the mode look like when I go super small radius? So here I prepare the same model, and the radius is 6 micron. So it's really tiny. And if you look at how does the mode look like already at 1550, you'll see that the mode is basically hugging the wall super strongly. And at some point, even for a high confinement waveguide like the one we use, that leads to some loss because, I mean, some of the mode is no longer confined. And the physical mechanism behind that is called bending loss or whispering-gallery mode loss. And it's going to look like that. So that's basically a microsphere, a small glass. You thin out an optical fiber, you melt the tip, and surface tension will force it into perfectly spherical shape. That has very high quality factor because it's very, very smooth. But you can't make it arbitrarily small because at some points the light just escapes. And the mechanism here is basically if you have a radius that is very small, you effectively you modify the refractive index potential, yeah. Basically by this let's call it centrifugal term that comes into play that forces the mode outwards. And what's happening is, so if your mode is here, then the effective mode index is basically that dotted line here. But because this centrifugal term basically at some point. So actually, the refractive index potential just in real world is a step potential here. But this additional term leads to the fact that somewhere out here, yeah, the effective refractive index in cylindrical coordinates basically dips below the effective mode index. And that means if you have an evanescent field out here, that field becomes no longer evanescent, but it becomes propagating. So it's basically the same effect. It's basically optical tunneling. It's the same effect you get in a beam splitter cube, you know. That's if you have a beam splitter cube, you basically have two high index materials and a low index material in between. And so the distance between the two high index materials will be fabricated in a way that 50% of the field can leak through the nonlinear index material and become propagating again in the high index material. So because here in this region you have an evanescent field, that means exponential decay of the field, and here it again becomes propagating. So this part of the field can actually leak out, and this leads to bending losses. So it starts to radiate outward, and that basically limits how small you can make a resonator. That limits how high Q you can retain when you make it small. That limits how high the finesse of the resonator, the field enhancement will be. Because, of course, the field enhancement increases a lot when you make the resonator smaller, but at the same time, you exponentially decrease the optical Q factor. What you will see is that there is an optimum resonator size if you optimize for finesse. And this is actually the exercise 3, if we manage to go that far. But if you have now a look at it, so again, one problem when you go to small radius, and that you will also see is if you look here, you start to get a lot of modes that look like that are not confined at all anymore. Yeah, so that's basically a mode that is reflected on the spurious reflection of the perfectly matched layer. You see it has a much higher refractive imaginary part of the refractive index, so it's super lossy. Yeah, I mean that's not a physical mode. But the mode which is physical, which has a lower imaginary part. But this imaginary part actually now has a meaning. This imaginary part is the radiating loss. So, and by basically solving this mode for different radii, oh, I don't have a parametric solution here. Okay, by implementing a parametric sweep here for different radii, you see that this refractive index, this imaginary part of the refractive index changes. And this gives you a so I go to exercise. No, there should be a solution. It's that one. Okay. No. This guy has the parametric sweep. Yes. So if I now go here, I have different radii. Oh, that's a field. Okay. So if I change the radius, this will change, and And from that, you can basically calculate the field. And the way you to make this change in the model is basically you need to include a perfectly matched layer. And so you would think of a perfectly matched layer as a boundary condition, but actually it's a volume condition. So it's not a boundary condition. You actually need to implement it physically as a part of your model. And COMSOL has a pretty elegant way to do that. It's just very well hidden, and you need to search a bit. But here in definitions, you can right-click, and here they hide the perfectly matched layer. It's here under artificial domains, perfectly matched layer. And here I made an additional, basically just on the outside. I mean, a bit more realistic would also be to also add a perfectly matched layer here on the top. And that increases the precision a bit. But most of the field will actually be lost here on the outside. And here I added another rectangle and just declared it as a perfectly matched layer. And what I also did, I used a, so if I plot the mesh of this, so perfectly matched layers really work best when the mesh that you use corresponds to the physical direction of propagation. So you want to have a mesh that's perpendicular to the propagation of the radiating field. So if you have an antenna and it's you have your antenna radiates into a spherical or semi-spherical world, what you want to do is you want to have a perfectly matched layer which perfectly matches the spherical symmetry. Here it's basically we have cylindrical symmetry, and so what we want is basically a mesh that also represents the cylindrical symmetry, and this can be done with the mapped node. So mesh, right-click, and then you get what's called a mapped node. And this mapped node then has a distribution property, and you can select the boundary, and you can tell this node that along this boundary I want to have 12 points, and or 15 or 20 points. And then there is like common design criteria for perfectly matched layers, so it should be on the order 5 to 10 lambda in wavelengths, in length, and it should have between 5 to 10 layers, and then it works pretty decently. And of course, all these parameters now should be subject to at least some rudimentary checks of the convergence in order to get the realistic values.
But who knows what is a perfectly matched layer? What is it about?
We change the equation. We amend our equation just to dump the waves on the border boundary.
Yeah,
exactly.
So this kind of absorption layer where you start to increase, your absorption, but you
So
increase smoothly, so that you get no reflection. More or less important.
Yeah.
Like a real
Okay, so the real part of the reflection index goes like this, and the imaginary part of the refractive index goes like this. Yeah. So that's the PML. So and usually you take an exponential increase of the refractive index because that gives you basically vanishing reflection, and this is the waveguide. So this is N.
Yeah, because what happens if you don't have
This is K.
perfectly matched layer on the boundary? You get back reflection, because in this case you have some perfect electric conductor or something like that. In like your mode is like it's confined between the waveguide and the boundary. But that's not physical.
Yeah.
It should be infinite, but you cannot make it infinite.
Okay.
That's why we use perfectly matched layer to absorb all
the radiative field. And this gives you, because now you have a non-zero K, and if you want to be careful, now you can go back to the materials here. And if you only want the bending loss, you should put in zeros here for the imaginary part of the material reflective index. Because if I put in here a 1, I will automatically get some absorption actually. Yeah, and that way you can basically model the absorption of your waveguide. And if you have one material that absorbs and one material that doesn't absorb, because one is like a high quality oxide and the other one is a low quality oxide, and one of them has basically some hydrogen in there that absorbs in the telecom wavelength band, you can manually change the values of this absorption to model that. And then as your mode changes, because the overlap with the different materials changes, also this would be factored into the absorption that you get as a function of frequency. But that is something in practice that we never do. So it's not necessary to get sufficient results. And so what I did here is I deleted the natural refractive index things, the natural refractive indices, the imaginary ones. So if the database has some absorption because glass absorbs it at low wavelengths, in there is I don't pull it over to the model, and I only get the bending loss.
That's interesting to see the mode distribution in log scale.
Yeah, true. Yeah, I've put it here. Okay. So here, if you have that's a Lint scale mode profile, so it hugs the wall, and the log scale profile. I mean, that's 10 to the minus 6 or 7 down here, but it's real. It's here, and then you see how it's absorbed in the perfectly matched layer. Yeah, and probably I should make it even a bit deeper, the perfectly matched layer, and maybe a few more points. Okay. Okay. Yeah. So we have made 3 exercises. I think you all got the. Is this the latest version of this presentation you have? I don't think so. I think I need to re-upload to the Google Drive. I made some changes yesterday. Exercise 1.
So we have 3 exercises. The first one is more or less like numerical to study the convergency. How your solution depends on the field size and the mesh size. That's why we parameterize it. Yeah, so we made these parameters of field and mesh, and now we can study how the solution depends on like which mesh you use, like fine, extremely fine, and stuff like that, and for which frequencies you use.
Let's see.
Like you have to choose which mesh and field size because it also depends on your frequency. Yeah, and the second exercise is more practical that you will use during the following.
Oh, I can't
That's
drag and drop.
dispersion linear.
Not.
And the third part, if you can manage.
I cannot. I will put up the third exercise here. Ansicht, Brillensortierung. I will put up the third exercise here. So the third exercise would be to use bending losses to quantify. I think Antonella or somebody needs to re-upload the models. Yeah. Okay, can we re-upload? Can I get access to re-upload the stuff? Because here I get an error. Not duplicate anymore. Extend. Can I get the... There's no way to show 2. Here to show 2. Okay. It's all on the Dropbox.